All right, everybody, welcome back. We are in Chapter 12 now. We're going to be starting our energy resources unit. And Chapter 12 is going to talk about non-renewable energy resources. That's what we're going to focus on first. Again, we're in Chapter 12 from Friedland and Relia's Environmental Science for AP. In Part 1, we're going to look at energy use and resources. So again, that's Part 1. We'll talk about worldwide patterns of energy use, then also patterns of energy use here in the United States, and then also a little bit on energy types and quality. And by the end of our first part here, we'll be able to describe how energy use and energy resources have varied over time, both in the U.S. and worldwide. So first, just to make sure everybody's on the same page, we want to talk about our basic terms, non-renewable energy resources. These are going to be our energy resources that we do not have a finite amount on. We have a limited amount, and once they're gone, they're gone. And both fossil fuels and nuclear fuels are considered non-renewable resources. Fossil fuels come from derived biological material that became fossilized millions of years ago. And our nuclear fuels are fuels that are radioactive, primarily. The main fuel is uranium. Also, sometimes depending on what kind of nuclear energy you're talking about or the use for it, plutonium as well. And just as a side note, it's very interesting. 10,000 watts of energy are used per person in the United States every day. 10,000 watts. It's a very staggering statistic. So if we first talk about worldwide patterns of energy use, just as, again, a quick refresher, going all the way back to freshman year general science, our basic unit of energy is the joule. And in terms of our prefixes, a gigajoule is 1 billion joules. And about 8 gallons of gas, that has the equivalent of about 1 gigajoule. And if we go even larger than that, an exajoule is 1 billion gigajoules. Okay, and altogether, all people all over the world, there's about 495 exajoules of energy use, which averages to about 75 gigajoules per person. And if we look at our graph that shows us that 81% of our energy use comes from fossil fuels, with a small amount from nuclear, and a little bit from renewable energy. And talking about the worldwide patterns of energy use, our graph here shows us two things. First of all, it shows us our total energy consumption, and then it also shows us our per capita annual energy consumption. Okay, remember, per capita is per person. Oops, let's just get rid of that. There we go. So if we take a look at the graph, we can see that the United States clearly uses the most amount of energy total. But if we look at the per capita annual energy consumption use, we can see that Canada uses the most energy per person. Australia is up there along with the United States as the most energy used per person. And Tanzania has the lowest energy use per person. What's also interesting to note is that if, depending on whether you're talking about a developed or a developing country, is the kind of energy that's being used. In developed countries, you're mostly talking about fossil fuels that are being used here, whereas developing countries more focused on wood, charcoal, and animal waste for sources of energy. And so moving forward, we're going to focus the rest of our time talking about the United States use, of energy. If we can get ourselves to the next slide. But first, though, we do want to talk about just two big categories here. First of all, commercial energy, and then subsistence energy. Commercial energy, that's the kind of energy that can be bought or sold, such as coal, oil, and natural gas. They can be harvested, extracted from the earth, and sold for commercial use. Substance energy, though, that's more on the individual basis, and that's energy that people are going to use and to gather for their own personal use, like wood, charcoal, and animal waste. And substance energy sources, that's going to be found, again, primarily by people in developing countries. So as I said, we're going to take a look at energy patterns, energy usage patterns in the United States. So we can see that before 1875 it was primarily wood, but from 1875 to the early 1900s, coal primarily took over as our main energy source. And then a little bit after that was the introduction of oil and natural gas, and we can see that those have steadily and gradually increased over the course of the years. We can also see that the use of coal went up, and then it went down, then it went back up again, down again. In the 1970s, there was a bunch of political and social and economic, environmental things happening in the United States, and our coal use fluctuated for a little bit there. We can also see that in the mid 1970s, nuclear energy came into play, and as well as hydropower. Hydropower has increased a little bit in the United States. Now, if we take a look at patterns of energy use in the U.S., we can kind of think of this as an input and input and output system, and there's a graphic that we'll take a look at on the next slide. In terms of our inputs, though, most of our inputs are from fossil fuels with coal, natural gas, and oil, and also nuclear and renewable energy. And our consumption, our energy use, it goes towards residential, commercial, industrial, and transportation purposes. And if you don't have this written down quite so fast yet, again, this slide here is pretty much the same thing, and it shows us that we've got our inputs on the left, and we've got our outputs on the right. Now, really interesting statistic is that the U.S. produces 70% of the energy it needs. But nearly 30% of our energy comes from other countries, and most of that comes from petroleum and fossil fuel imports, and you can see that down here at the bottom. And we're going to kind of come back to this a little bit later on, but we can see that most of our energy consumption goes towards industrial purposes, but also a significant amount towards transportation, and then commercial and residential uses are almost even on the right. If we take a look at this slide, again, talking about patterns of energy use in the U.S. and our graph here, we can see that total we've got 105 exajoules that are used, and 84% of the energy used in the U.S. comes from fossil fuels, primarily oil, and then closely second and third are natural gas and coal. About 7% of our energy comes from renewable sources, and 9% from nuclear. Also want to talk about energy types and quality now. So depending on the energy source, you're going to have a different kind of energy or different source of energy that you're going to want to use for a different purpose. Case in point, if you're talking about transportation, liquid fuels are preferred for transportation because they are relatively compact, they're very quickly combustible, and they have a lot of energy in their chemical makeup. Okay, and if you were to try and power your car and drive your car on wood and burn wood instead as your fuel, it would take a lot more wood. The volume of wood that you would need would be outrageous, whereas your liquid petroleum, gasoline, is very quickly combustible. So again, energy sources are fitted for their use. And when we talk about energy efficiency, we want to make sure that we talk both about the process of obtaining the fuel and the process that converts it into work. So we're going to talk about the process of obtaining the fuel next. And then our energy return on investment on the slide after that. But again, when we talk about efficiency, we need to make sure that we understand that we're talking about how efficient is the extraction method of obtaining the fuel, and then also the process that's going to convert that fuel into actual work. So our process of obtaining of energy starts on the left, with our energy resource being extracted. It needs to be transported somewhere, processed, refined, and converted and that will usually be used to generate electricity. We can see the electricity transmission through the power lines and then eventually to the person. And we can see that all along the way we've got those red arrows, and those red arrows are our energy losses. And that can be in a wide variety of form, anything from heat to pollution, particulates, and carbon dioxide emissions. We briefly touched upon over the summer when you looked at Chapter 2, one of the laws of thermal dynamics, whereas energy can't be created or destroyed, but it changes form. So this is energy transformation here. This is the process of energy transformation. Energy is transformed all along the way, and so we can see that we do lose a lot of heat, a lot of energy. We lose a lot of it in the form of heat along the way. Coal power plants are only 35% efficient, so that means that only 35% of the energy that's is converted and used by the person there, the consumer, that was originally started with when the coal was back in the ground. Talking about energy return on investments, there's a formula here, and so the energy return on energy investment is, we can find that by taking the energy that's obtained from the fuel, and we can divide that by the energy used to obtain the fuel. So, for example, if the energy used to obtain a fuel, in order to obtain 100 joules of coal from a surface coal mine, 5 joules of energy are expended. So then if we do the math there, that would give us a value of 20. And the larger the value, the more efficient the system is, the more desirable it is. And we'll have some practice with that as well as we go through the chapter. We also quickly want to talk about energy types and quality. We can take a look at the megajoules per person, per passenger per kilometer used, and we can see that motorcycles and trains are going to be the most fuel efficient here. We can see that buses are a little bit less efficient, and the worst efficiency here you can obviously see that is driving alone in a passenger car. This graph shows us the fuel efficiency of U.S. automobiles throughout the past 30 years or so, and we can see that there was a huge increase in fuel efficiency in the early 1980s, but we've pretty much kind of leveled off. We're at the same point now where we have been. There was recent legislation, though, that was passed, and that's going to, by the year 2016, that's going to increase fuel efficiency of new cars and light trucks. So we should have a fleet average of 35 miles per gallon by 2016. So that was new legislation that was passed. What's also would be interesting for you is to compare this graph to the graph that we saw in the DVD, An Inconvenient Truth. Compare this graph here to the average fuel efficiency of U.S. automobiles versus the fuel efficiency of world automobiles across the world, specifically in Japan. It's quite an interesting comparison. And so we can see that, quick little explanation, from 1990 to 2005, more people chose SUVs and light trucks as their vehicle of choice. And as I mentioned before, we've got our legislation there. So we've reached the end. We've reached our checkpoints. First checkpoint, what are the 3 examples of energy sources used by humans? Number 2, describe the difference between energy efficiency and energy quality. And number 3, how do we determine the overall efficiency of energy use in a system? So take some time now, go back through your notes, read the chapter, get all your answers prepared so that when you go to Edmodo, you can answer these questions, because again, you'll only have about an hour or so. And once you open the questions in Edmodo, your time starts. So make sure that you've got the questions here. They're up on the screen. Just hit pause, and then when you're ready to actually type out your answers, go back into Edmodo. This is it for part 1 in chapter 12, and once you're finished here, you can move on to part 2.